It's true. This is the definition of the limit of a function. I will refresh our memory. Limit as x goes to c of f of x equals L. This means, the definition is, there's like an epsilon's version of this definition. It means for all epsilon greater than 0, there exists delta greater than 0 such that 0 less than absolute value x minus c less than delta implies absolute value f of x minus L less than epsilon. So this is the definition of the limit of a function. This you definitely should memorize eventually, I suppose. I mean, you're going to be doing it often enough, but I will expect you to know this definition. There's a lot of symbology to it, but basically this part over here means when x is close to c, and this part over here means f of x is close to L, right? So in that informal kind of language, it says when the x is really, really close to c, then the f of x is really, really close to L, which is what this limit means from an informal point of view. All right, we did some examples last time. There's some more to try on the homework. I did one example at the end which uses sort of a special trick. I thought we'd try one more like that, and then I got one for you to try, which is of the same general nature. So 2 more examples. Actually, and then I got yet another example after that, but whatever. Let's try, for example, lim x goes to 3 of 3 over x equals. First of all, you have to say what the limit is and then prove that that's actually the limit. What should the limit be in this case? 1, yeah. You can generally find the limit, as you learned in a calculus class. You can generally find the limit by just plugging that number in. It's 1. So let's try and actually prove that. So I begin with let epsilon greater than 0 be given. And then we'll find delta such that 0 less than x minus, I'm just rewriting the definition here, x minus c, the c is the number 3 in this case, less than delta implies, and here I say f of x minus L, that would be 3 over x minus 1 in this case, less than epsilon. All right, that's just stating what we are going to do. Now, as usual, I'm going to do a little sort of work in red here, which is going to be simplifying. So I start with the thing that I want to end up with being less than epsilon, and you have to simplify that with the hopes of factoring out or solving for absolute value x minus 3. I would like to solve for absolute value x minus 3 here. Anybody want to suggest what I can do to simplify here? Yeah. Yeah, we should make a common denominator so that we can actually add the fractions here, or subtract the fractions. So this is 3 over x, and he suggested, and I think it's a good idea, turn the 1 into x over x so that I can subtract. I get 3 minus x up top over x, like so. All right. I would like to somehow factor out or solve for x minus 3. Is there any way to get that from here? One thing I can do in a fraction is just make absolute value on the top and on the bottom. That's usually helpful. So I'm going to make absolute value x and absolute value 3 minus x.
Are you allowed to, I'm not sure if you can, but are you allowed to do like the less than and then just get rid of the x? Because if you get rid of what you're dividing by, it must automatically be given.
This is a good idea in general, and the answer to the question, am I allowed to do that, is generally speaking, yes, although you can't in this case. She's suggesting just say this, because I'm not dividing by x anymore. But there's an issue with that, is that this x, you don't know what it is. It could be any real number, actually. And therefore, it could be something like if this x is less than 1, then actually dividing by it will make it smaller, so throwing it away doesn't necessarily make it bigger. So that, can't do that. Yeah.
Should you separate it so it's like 3 minus x times 1 over x?
Sure, yeah. I would like to, this is a good idea, so I am going to do that. 3 minus x, and then also 1 over x. I want this though, absolute value x minus 3. Can we make that appear out of here somehow? It's actually, we did an example like this last time with this same.
Isn't 3 minus x the same as x minus 3?
Yes, in the absolute values, 3 minus x is the same as x minus 3. So that's how we, I mean, it just is. The absolute value x minus 3 is the same as the absolute value 3 minus x because they are opposites of one another. One is the negation of the other. So inside the absolute values, they're the same. All right. This actually is as simple as you can make this at this point. Now we have to do a kind of trick which I did one example of last time. This kind of trick does not come up when you're doing sequences, so this is sort of like a new kind of trick for functions. And it is the one where we are assuming that x is kind of close to 3, which means 1 over x is kind of close to 1/3, in which case this I can just replace by 1/3. Now you don't say that exactly, but x is kind of close to 3. So let me say we're going to assume, or I'm just going to say if delta is less than 1, then absolute value x minus 3 will be less than 1. That means, if you prefer, so that means x is between 2 and 4, right? You think about if x is close to 3. Now I said 1 just kind of out of nowhere. This 1 is not terribly important. I could have said if x is less than a half, then the x is between 2.5 and 3.5. That doesn't really matter. You might as well just, in most cases, you can just take the delta to be less than 1. Anyway, x is between 2 and 4, and now we can do something like she suggested. She suggested just throw the x away. You can't do that, but the x is between 2 and 4. So this, with a less than or equal, 1 over absolute value x is less than or equal to something, right? Less than 1/4, a half, which something like that, since the x is between 2 and 4. Yep. Which one is it? Is it 1/4 or a half? I want to basically plug one or the other of these numbers in for x. I'm trying to think of the biggest that this could possibly be. I would say 1 over x will be as big as possible when the x itself is 2. Yeah, right. So this, I say, in red here, this, right? 1 over x is as big as possible when the x there is as small as possible, which is the 2. This sometimes can be a little tricky. You gotta slow down and make sure you're thinking properly about which way around the inequalities are going, but this is the way it goes. Okay, so in this example, all of this means this part here I can say is less than or equal to absolute value x minus 3 times a half. All right? Because the 1 over x part is less than or equal to 1/2. And now I can continue as we usually would. So I want x minus 3 times a half to be less than epsilon, which is to say x minus 3 to be less than 2 epsilon. So I'm going to let delta be, well, something less than 2 epsilon. All right? This is how we finish the sidebar. This is, of course, where most of the hard work happens, really, in the sidebar, just like when you're proving limits of sequences. All right. Anyway, let's just finish writing the rest of the proof. We have to begin by saying I'm going to let delta be not what I just wrote. It's not quite. It's because the delta, in order for all of this to work, the delta has to be less than 2 epsilon, and it also has to be less than 1. Anybody remember how we write that all sort of at once here? We did this once last time. Yeah. Right, I say let delta be less than the min of 1 and 2 epsilon. So that means delta is automatically going to be less than 1 and also less than 2 epsilon. That way we get everything in the box up here will be true just the way we said it. All right, so I will just finish writing the proof. Then if x minus 3 less than delta, we have I start with 3 over x minus 1, right? This, following the simplifications, I can say first of all is equal to x minus 3 times 1 over x, right? Zoom it. And then this is less than or equal to x minus 3 is less than delta, and delta is less than 2 epsilon. And 1 over x, because delta is less than 1, is less than a half. And this is epsilon, as desired. All right, that's how it goes. So this is the old delta equals the min of 1 and something else trick. All right. Any thoughts about that one? I got one, a similar one for you all to try. All right, let's try it. Let's see if you really understand it when you go to try one. So how about lim x goes to 2 of x squared equals 4. See if you can work that one out. It should be similar. Kinda. I'll give you a few moments and then I'll come around and see how you're doing. You can write the beginning without thinking about anything. You just have to remember. The one we just did, I wrote in blue.
She did some example.
A little harder to see because it was in the denominator. You have to use the other one. All right. This means the way that I think of this is this is
Well, I'm trying to look at this.
So let's do those two negative two. What are supposed to do minus 6?
Yeah.
Yeah, this means that the distance from x is all right. So you want to do this like assume the delta is less than 1 thing. So the x minus 2 you already have here. So that part you should throw out. This is good. This is a problem. And the thing is, if x is supposed to be close to 2, then x plus 2 should be something like 4. You can't say that exactly. So that's too hard. To say that properly is you say something like, well, okay, if x is closer than 1 to 2, then this has to be something like within 1 of 4. So that's why you say if delta is 1, that's plus 1 and the distance from x to 2 is 1. So that's plus 2. No, it's not. This part is not small. This is like something like 4. This part is like 0. Like this part is like 4. So you're going to replace it with a constant. And then divide out the constant at the end. Yeah, that's it. Okay? All right, let's talk about these. I see some people did great and some people kind of got stuck in the middle here. This is how you should begin, regardless of if you know what you're doing or not. That's the way to start. And then it's like this, right? And I have to simplify here. And what you do is factor. So this is x plus 2 and x minus 2. And you might as well separate it out. I just wrote them in the other order for some reason. I don't know. I like the x minus 2, right? This is what I want to see in there. This is extra business that needs to be dealt with. So really my goal is to say this is less than or equal to x minus 2 times something here. Sort of fill in the blank. What is x plus 2? What is an upper bound for that x plus 2? That's what we need to fill in. And the way to do this is with that thing about let delta be, so if I let delta be less than 1, then you can say, where is, what's the range for x? Then x minus 2 is less than 1, right? This means, the way that I think about this is, this means that x is within distance 1 of 2, right? The distance from x to 2 is 1. So that means that, well, it means this, doesn't it? Right? X is between 1 and 3. You can, if you like, if you prefer, you can draw a little picture of that. Here's 2, and then x is in here somewhere, right? Where this goes, this distance here is 1, right? So x is between 1 and 3. Now, I'm not really interested in x per se. I'm interested in x plus 2. But you can just add 2 throughout this whole thing. So that means 3 less than x less than 5. Sorry, x plus 2 is what I'm doing. I'm adding 2 throughout that inequality. And this is why I can replace x plus 2 here with a 5 here. That's what we end up filling in. The other half of that inequality is not important. It's this one that I care about. X plus 2 is less than 5. And so, I mean, also in absolute value, x it's going to be positive, right? It's between 3 and 5. So the absolute values don't matter at that point. And so that means this thing here, I can say this is less than or equal to x minus 2 times 5. That's how you do this trick. This is a little tricky trick. Anybody got any questions about that? Thoughts about that? I mean, if you were going to get messed up here, this is probably the point at which it would happen. Yeah.
So, where did we get the 1 less than x less than 3? Why do we know that?
Yeah, it's right here. So if the delta is less than 1, it means x is within distance 1 of this value 2. And so it has to be in this range, 1 unit away from 2. And so that's where this comes from. Right, the biggest it could be would be 1 more than 2, which is 3. The smallest it could be is over here, is 1. Another way, I don't know if you prefer this, another way to explain this, which to me is maybe a little more confusing, but if you prefer, you could say x minus 2 less than 1. This is the same as negative 1 less than x minus 2 less than 1. This is a way of getting rid of the absolute value signs. Saying that something in absolute value is less than 1 means that it's between 1 and minus 1. And then if you just add 2 through the whole thing, it will say 1 less than x less than 3, which is what I said over here. So this is another way of coming up with that without thinking. If you prefer to just work through equations the whole time, this is a way you can arrive there. Although, to me, that's a little more confusing, but I prefer to think of it in terms of this little number line picture. All right. Yeah.
Do we want to add 2 and make it so that we get the x plus 2?
Yeah, that's right. Yeah, I added 2 so that it would match up with this, which is what I'm trying to deal with in my inequalities. Yeah. All right, so let's just finish writing the proof then. So that's all the sort of scratch work. I say let delta, what do you say here? Delta be less than?
Min of 1 and epsilon over 5.
Yes, the min of 1 and epsilon over 5, right? Epsilon over 5 because I ended up getting here x minus 2 times 5. So when you sort of solve for delta in that, you get epsilon over 5. Yeah, great. And then I can just say, then if x minus 2 less than delta. We have x squared minus 4. Of course, this equals x minus 2 times x plus 2. And that is less than or equal to epsilon over 5 times 5, which is epsilon. All right, that's how it's done. You will have some more of these to try on the homework. So this, I think, these are a little confusing, although they are formulaic enough that I think doing more examples will help to get the basic idea in your head. You just have to know which tricks to do. All right? Great. I got one last example, and then we will move on to something a bit different. So this is really the same trick, but kind of amped up a little bit, I guess. Let's try lim x goes to 2 of x cubed. Huh? How you like that? We just did x squared. This is x cubed. Totally different. Equals 8, right? Let's see if we can try that. All right. Same opening as always. Let epsilon greater than 0 be given. We'll find delta greater than 0 such that, all right, x minus 2 less than delta implies x cubed minus 8 less than epsilon. All right. Okay, let's, try not to think too hard about this. You just got to get it started. Simplify x cubed minus 8. Any ideas here? Yeah.
It's 2 cubes, right?
Yes.
X minus 2.
Yeah. I'm impressed that you remember even that. There is, the moral of this story is, sometimes you got to just use like random facts that you learned when you were a kid. And the random fact in this case is, there is a formula for the difference of 2 cubes. And you can use that to factor this. Anybody actually remember that formula? I don't expect anyone to actually remember that.
It's like square.
If I have something like a cubed minus b cubed, what he said, it's a minus b times some other stuff.
A squared. Take the square, put the product with the square. Minus a square product square, and then you have signs.
It's like pi r squared, mc squared. This is what it is. I like when people just talk random nonsense. I have no idea if what you said is correct or not. I can play like Dora. I'll be like, yes, you're right. When Dora asks you to do something, she always says, good job.
That's very good.
Dora doesn't know if you were right. She just says it. All right, that's the formula. So that means I can simplify this to be, first of all, x minus 2, right? In this case, the a and the b, the a is x and the b is 2, because 2 cubed is 8, right? And then the rest of it, I'm splitting up as absolute values also. X squared plus 2x plus 4, all right? So, first moral of the story for this example is, sometimes in the simplification step, you have to use some random fact, which you may or may not remember, all right? In this case, it's something about the difference of 2 cubes. If your function is something like, sine x or cosine x, you might have to use some weird formula involving sines and cosines to try to simplify out the part that you're talking about. Okay, anyway, can we continue from here? Now, this is, we're still not totally good at this point. Like, I feel good about this. This is good, right? Because I'm trying to end up with x minus 2 in absolute value. So that part I like. It's the rest of it here I have to deal with somehow. You got ideas? No. Oh, I thought you were. You got it?
To be x plus 2 is plus 2.
Factor this is a good idea, but actually those aren't the right
You know
factors.
what? Factor it and then forget
Yeah.
the last time.
Actually, this does not factor, unfortunately. It would be nice, yeah, but it don't factor. Any other ideas? I'm gonna do the old let delta be less than 1 trick. It still is gonna work here, all right? It's just a lot more complicated to decide what is bigger than this thing, all right? So in the last example, we replaced this part with like 5, right? We just have to figure out how big can that possibly be. So I'm gonna say let delta be less than 1. And so that means in terms of the range of values where x is, what can you say? X is between something to something? Yeah, 1 to 3, right? That what I'm talking about is here's 2 and x is near 2 at distance 1 away. So it has to be in that range. So x is between 1 and 3. All right? Yes?
How do you decide that? Is it like a constant thing, or is it just like
How do I decide to use a 1 here, you mean?
what the like range is?
It's just because the meaning of delta is delta tells you how far away it is from 2. And if I say delta is going to be 1, it means it's that far away from 2. 1 on either side. Yeah. Okay, so x is between 1 and 3. So now you should be wondering, all right, then what's the biggest possible value this could be? And apparently you should be able to figure that out, right? This is a parabola. In the very worst case, you could use some kind of calculus to find the maximum value of this parabola on that interval, right? Although, by the looks on your faces, I feel like you don't really want to do that. But that's in a very complicated example, that's what it would come to. Although in this case, we can get around that a little bit. Anybody agree with me? I feel like I should just plug 3 into that and be done with it, right? Although, are you sure that's actually the biggest value of this? Yes? I mean, on a function, ordinarily, it's not true that the biggest value is like furthest to the right, right? This is a parabola. I mean, could it be that we're on the downward part of the parabola at this point, so that the biggest value is actually on the left side rather than the right side? What are you saying? No. Why not? Because you know where the vertex of that parabola is, and it's to the right of 3.
Isn't it like up 4 and then like a 2x just makes it wide? So it's like just like a wide parabola that's up 4.
Nah, the vertex of this parabola is not at the y-axis, right? It's somewhere else. To tell if we're on the downswing or the upswing, you have to know which side of the vertex this is on, right? It's a little complicated. Actually, there's a little workaround we can do here by playing with this inequality. So I'm going to use the triangle inequality here. I will just, maybe in a blue box, I will put the triangle inequality. It's just this. Sorry, less than or equal. It's that, right? When you have things added in an absolute value, it's less than or equal the sum of the two things. And so this thing here, the parabola part, I'm going to, maybe I'll just, oops. I will continue down here. X minus 2 times this parabola thing. Using the triangle inequality, I can say this is less than or equal to absolute value x squared plus absolute value 2x plus absolute value 4. I split the absolute value of the second part up into those 3 bits. I suppose I use the triangle inequality twice. All right? And now, can we simplify that at all? Well, I mean, absolute value 4 is 4, okay? Absolute value 2x, I could factor the 2 out of that. So this is actually equal. I'm not doing more inequalities here. What about x squared? Absolute value of x squared, isn't that the same as this? Absolute value x squared, right? Plus 2 absolute value x plus 4. Okay, and now I think it is clear that I can just replace x's by 3's and everything gets bigger, all right? It was not so obvious before, although you all seem to think it was obvious. I don't think it was obvious. This is something weird about mathematicians often spend a lot of time arguing about what is obvious or not, even though something's obvious, you shouldn't be arguing about it. It's a common thing. You probably experienced this talking with math, trying to do the homework or whatever. Someone else is like, yeah, oh, that one was easy, and then you try to do it for an hour, and then you realize, oh yeah, it was easy, even though it took you an hour to do it. Anyway, this is now I can say this is definitely less than or equal to x minus 2, and then I just replace all those x's by 3's. So 3 squared plus 2 times 3 plus 4. And that is 19. And so I'm going to use epsilon over 19. This is actually fairly common in proofs like this. You end up with some really weird constant at the end that comes from doing some strange simplifications in the middle somewhere. All right? But this is just an example where you have to do something a little fancier in order to figure out what this constant at the end should be. Yeah?
If you had a subtraction in that quadratic, would it use the triangle inequality still, or would it not?
Yes. No, that's the beauty of this approach is even if this had minus signs in it, you can still do exactly the same thing, and it'll work. I mean, you'll end up with 19 again if these were subtracted. But it'll still be valid. That's the good thing. All right. So let me just, we should actually write out the rest of the proofs. I'm going to say let delta be less than the min of 1 and epsilon over 19. Then, now I just write all my usual stuff. X minus 2 less than delta. We have x cubed minus 8. Okay, this equals x minus 2 times this stuff, x squared plus 2x plus 4. That's less than or equal to x minus 2 times 19 by the arguments that we did up there. And then this is less than epsilon over 19 times 19. All right, so this was just a slightly fancier playing around with the inequalities. Any thoughts about that? Any questions? Great. Yes?
When we end up with a constant like that, and we have x minus 2 times 19,
Yeah.
will it usually end up being epsilon with that?
Yes, it must. I mean, the reason, yes, because the reason I put epsilon over 19 here, this was like my own choice. You can choose this to be whatever you want. But I chose epsilon over 19 specifically so that it would cancel here. So they will always be the same number if you did it right. Yeah. Yeah, great. All right. This is all the examples that I wanted to do of proving a certain limit of a function equals whatever it equals. All right. For simple functions, this is not so hard to do, but part of why I wanted to do this example is just to show that if they're even slightly complicated functions, this can be very, very hard to do. I just did x cubed, and it relied on the fact that I knew this random formula. What about, could you do a similar, I like to feel like something like this, right? Like that should be, from a certain point of view, I feel like, shouldn't that be just kind of like the same as what I just did, only it's a 10th power instead of a 3rd power? No, it's not the same, because you need to know whatever appropriate trick is to deal with the 10th power. And I don't know such a trick. Like there is such a trick, but if you modify this function a little bit, things get quite a bit more complicated. Actually, if I had to prove this, probably I wouldn't even try to do it directly like this. I would say something about the fact that x to the 10 is a continuous function, and so I can just plug the number 2 in. Although this is stuff that we haven't talked about yet, but that's where we're going to go eventually with this. We're going to talk about how if the function is continuous, you can just plug the value in, which is something that we all learned in calculus class.
So when you use like less than versus less than or equal to, is there like a certain?
My answer would be, if you want to be safe, you could just write less than or equal to every time, because if something is actually less than, it is also true that it's less than or equal. But if something is equal, then it's not true that it's less than. But basically, I use less thans. It is important to use a strict less than here. That less than should not be a less than or equal. Otherwise, I think it doesn't really matter. By which I mean, you should probably just write less than or equals. And like part of the definition has to be less thans, strict less thans. Yeah. This is mostly a technicality that doesn't really make much of a difference. Yeah. It's good to be careful about it though. And actually is a little confession I have. This is the second time that I've taught this course. And the first time I taught it, I constantly messed up less than versus less than or equal. And I always said, it doesn't really matter. It doesn't matter anyway. But I was doing it wrong all the time. And I posted those class videos on YouTube. I don't know if you ever saw it. There's like another version of this class from 2 years ago. That's somehow, huh?
Behind the glass.
Yeah. And somehow those videos got like a lot of views from the internet at large. But they are constantly making comments about, shouldn't that less than be a less than or equal? And I would say yes. Sorry. That's all right though. Okay, we got 8 minutes remaining. They're usually kind about it though. They're not too. I don't get a lot of angry comments. One more thing to say, which we will talk a lot more about next time, and that is a sequential criterion for limits. It turns out that limits of a function, you can rephrase the definition of a limit of a function in terms of limits of certain sequences. All right. So I will just write down what the statement is first of all. I don't want to do a proof of this. It's actually fairly straightforward to understand. This is true. So this is the definition that we've been doing today. For all epsilon greater than 0, there exists delta such that x minus c less than delta implies f of x minus L less than epsilon. All right, this is true. This is equivalent. I'll put a big old double arrow here. This, if and only if, something that I'm going to write about sequences. It says for all sequences, let's say xn, which approach x. C is what I meant. Wow. For all sequences xn approaching c, we have f of xn approaches L. All right. These are actually equivalent with one another. Really, this is a theorem, although, like I just said, I don't really want to talk about the proof of this. What this says over here is, this is really another way of saying it just in terms of sequences. If I choose numbers which get closer and closer to C, I think this really encapsulates the whole closer and closer attitude for those people who somehow believe that a number can get closer to another number, which it can't, but a sequence can get close to another number. So it says, if you have a sequence of x values and they approach C, just like this, then the sequence of function values approaches L. That's the same as this over here, the limit as x approaches C of f of x equals L. All right, these are equivalent. So the picture, if I were to describe each of these in pictures, the picture here is something like I drew a picture last time. If this is C and then this is L, it means that all of the x values sort of within this little window here, their y values go within this little window here, where this radius here is delta and this radius here is epsilon. All right, that's kind of the picture that I have in mind for this definition as we wrote it today. Whereas the picture that I have in mind for the definition over there, they are equivalent, is I'm going to draw the same function. I have C here. Oops, in black. And L here. The picture from this point of view, from the sequential point of view, in terms of sequences, is I imagine, say, a bunch of points here which are approaching the C. These are the xn's. It's a sequence of points which approaches the C. And what does it mean that f of xn approaches L? Well, it means each of those points on the sequence goes up to some value on the curve. And if I look specifically at those y values approach L. So these values here are f of xn. So if I have a sequence in the domain which approaches C, then that makes a sequence in the range, in the codomain, and that sequence of points approaches the L. All right? This is the sequential criterion for limits. The limit of the function equals L is the same as saying for any sequence approaching C, the f of that sequence approaches L. All right? Now, the one on the right is actually pretty bad to use to prove that a limit of a function exists. If I have to prove the limit of a function equals something, I'm going to use the one on the left every time. But actually, the one on the right is very convenient to prove that the limit does not exist. The one on the left is actually not very easy to use to do that. So proving, I'm just going to say we use the sequence version, the one on the right, to show that some limits do not exist. And maybe I will just leave it at that for today. We're going to do a bunch of examples with that next time. You can, in theory, use this version to show limits do not exist, but you have to negate this whole definition, which is very complicated with the negating of the quantifiers. The one on the right, though, is actually quite easy to use for that purpose. All right, see you all tomorrow. We do have homework due tomorrow. Let me know if you have questions.